So my name is Spencer. Today I will be talking about common NGINX misconfigurations that leave your web server open to attack. I currently work as a researcher at Detectify based in Stockholm. We just did my bio, so we can skip over that. Here's a brief agenda for today. I'll just go over quickly what we do at Detectify, go over how NGINX works, the methodology we use to get all of our files to analyze, and then I'll go into the main misconfigurations that we found on our team. So first, Detectify is an automated web scanner that uses the crowd to find vulnerabilities in common technologies. So white hat hackers from across the world will submit POCs to us. We'll then triage and build those exploits into modules, and then we'll run those modules on our customers continuously. And unlike HackerOne or Bugcrowd or other bug bounty platforms, we reward our hackers based off the number of hits each module will produce in perpetuity. So now we can go into NGINX. It is a high-performance web server, reverse proxy, load balancer, and much more. It really does everything that you need it to for a server. It's extremely fast. It can manage incoming traffic and distribute that among different servers to maximize speed without degrading performance. And it will just handle tasks that otherwise would slow down your web server. About 1/3 of websites use NGINX, which make it a very popular technology for customers as well as attackers. The pros of using NGINX are it's highly modular, very fast, easy, very configurable, but the problem and the main con with that is that it's very easy to misconfigure. So our methodology to analyze these files was first to use Google BigQuery to download 50,000 approximate NGINX configuration files. BigQuery allows you to run complex analytical SQL-based queries on large sets of data on the order of billions of rows at a very efficient speed as well as price. And we're using the return values from our query. We were able to construct downloadable URLs. So if we see in our example to the right, it's very much looking like SQL. We select the repo name and path from the public data set that GitHub has on Google BigQuery. And then we want all the repos that have paths that contain the nginx.conf file. So then from there, we were able to construct downloadable URLs, the raw files from GitHub by appending the repo name, branch, and path. And then from there, we downloaded the files and then use shell tools to find patterns that would indicate the presence of certain misconfigurations. So now we can dive into the first misconfiguration, which is called missing root directive. The root directive specifies where to look for files and which files to serve. So in our example to our right, we see our root directive goes to etc nginx. However, it does not have a location for the roots. Therefore, the root directive will be globally set, and any request to the root of the application will deliver files from etc nginx. So if you make a request to localhost/test, the nginx server will then serve the file from etc nginx test. So in a real world example, you could request localhost nginx, and that would then serve the file from etc nginx directory. So the impact is that it has access to sensitive files on the server, and you can assume anything in the path can be read if it's placed in the root directive. And depending on the misconfiguration, it's possible to reach other configuration files, access logs, or even encrypted credentials for HTTP basic authentication. The remediation is pretty simple. Just use specific paths when using root directives and ensure they do not contain any sensitive files. Misconfiguration 2 is off by slash. So in order to understand the vulnerability, it's important to understand some of the background behind it. So the intention behind location directive and the alias variable is to create an easy alias to use in requests to replace long paths on the nginx server. So if the client were to request something like static index.js, nginx would know to serve a local file from user share nginx static directory, as we can see in this example to the right. Likewise, if we make a request to API/test, Again, it's to lead NGINX to request and serve from API server v1/test. Now, the cause of this misconfiguration is the lack of the directory separator after static and API. As we can see here, there's no following directory separator. And this misconfiguration, though very small, can lead to directory traversal. So here, we'll see NGINX look for matching location. So when we make a request, it will remove the prefix API and append the rest of the URI to the directive in the location block. So when the directory separator is missing, as we see here, it then becomes possible to traverse only one directory up by using .. or the off// technique. And before going into the demo, just wanted to show a quick example of how off// is a bit more nuanced compared to path traversal. So I believe you can see this file. So here in a normal path traversal, we make a request to localhost v1, and we know that there might be some sort of secrets file in the local host directory. So normally with path traversal, we would just go to v1, as we see here. We have the / that follows it, and then traverse one directory up, and then go into the secret folder. However, with the off//, we do the same thing in a way where we make the request to localhost API. We know that because of the alias directive, it really gets converted to v1 on the NGINX server. So when we try to do our path traversal exploit, we do something like this. So instead of we don't have the / following the API, we just do a simple .. as you see here, and then NGINX will see that and configure it properly and traverse one directory up and then go into our secrets directory. So now we can go into our demo that shows how to exploit that on our basic cat application. So here we have our cat application. We go into our NGINX configuration file. When we scroll down, we see how we have a location directive that points to a cat pictures directory in our Apache folder. So now when we make a request to our image to that JPEG file, we see in the bottom right that it really makes a request on the back end to cat pictures to .jpeg. And that's because of the location directive in our configuration file. So now we'll go into our Apache folder. We'll see in that folder we have the secret HTML file as well as the cat pictures directory. So we know we can possibly traverse one directory up and try to get access to that secret file. So here in burp, make a request. We see how it then converts it to cat pictures in the backend. So we'll try that normal path traversal technique, and we'll see how it will not work because we have that / following image. So instead, to traverse one directory up, in our next request, we'll just remove that / following image, and that should allow us to view the page, as we can see in the response in burp. So now that we have that, we'll then make a request in the browser just to show what that looks like in an actual attack. So we'll copy the URL from burp, make a request to the image, and we see now that we have access to this secret file. So the impact is the alias directive tells NGINX the location to look for the file. So off// plus the alias means that it's possible to read the files one folder up. This can allow an attacker to read files stored outside of the target folder. The remediation is just to append the enduring directory separator to the location variable whenever there is an alias directive. So just as a reminder, misconfigured is just having the location directive with no / after static Then adding it after static makes it properly configured, and you can avoid that off by slash attack. Configuration 3 is CRLF injection via the URI variable in NGINX. So CRLF injection is the ability to inject new lines into HTTP headers, effectively allowing you to inject your own headers into the response. So the URI is a built-in variable in NGINX that contains the request URI, and it will automatically URL decode the values, including the carriage return and line feed characters. So in our configuration to the right, it'll redirect the user to another domain. So if we make a request to nginx.com/test, it'll take the URI following the domain, append it to example.com, and then redirect it that way. So before going into the actual vulnerability, it's important to really understand new line characters in HTTP and how URL encoding works. So new lines in HTTP consist of the two non-printable characters \r or \n, which is carriage return and line feed. And we can see to our right that each header in the request and the response are separated by those two characters. A common encoding for characters in HTTP is URL encoding. URLs are designed to accept only certain characters in a standard 128 character ASCII character set. Special characters not being used for their intended purpose must be encoded, and each encoded character is represented by a % followed by the ASCII hex value. So if we were to type hello there in the URL, the encoding for the space and exclamation mark would be %20 and %21. But for our purposes for this attack, we only care about the carriage return and line feed characters, and those encoded in URL would be %0d and 0a. So %0d and 0a are URL decoded and reflected in the HTTP headers. We can add our own headers or even our own body in the response. So again, looking at our previous misconfiguration, if we make a request to localhost and then we add our return characters and line feed characters after that, and then we inject our custom header, the URI variable will automatically URL decode those characters and inject our Detectify custom header in the bottom, as we can see in the bottom right of the example. So now we'll go into our demo to show how that works. So here is our cat application once again. We turn on the intercept and burp, so we make our request to image credits, send that to repeater, and we'll look to see if the path in our GET request is reflected anywhere in the response, which it is in the original path parameter in the location header. So now we'll add an extra path to see if that's also reflected as well. We see that it is. So now we can try to add in our carriage return and line feed characters to potentially inject new headers into the response. So we see here how each header is separated by those two characters. So we go to CyberChef, and we can show how if we type in hello there, they're separated on two separate lines. So now we'll add in our own custom header and URL encode that and try to put that in our GET request path and see if we can inject that header in the response. So now we encode it. We grab the outputs and then put our payload now in the repeater. And now we see on line 8, we were able to actually inject our custom header into the response. And now we want to take this one step further and see if we can actually add our own custom body into the response. And to do that, we'll have to add 2 extra characters or an extra pair of line feed and carriage return characters and have those encoded as well. And we'll add that to our GET request. And we'll see how now we're able to inject our new body in the response. So the impact is we're able to inject arbitrary headers into the HTTP response. We can serve malicious pages to the end user. We can execute XSS and potentially leak sensitive information into the body. As we just saw, we were able to inject our own body into the response. So if we can potentially do that with headers, we can leak sensitive cookie values into the body and then access those. The remediation is to just use the request URI instead of the URI variable. The request URI variable contains the unprocessed original URI and will not decode the values that we just have. So our last misconfiguration is proxy pass via regex. When NGINX proxies a request, it will send the request to a specified proxied server. It'll fetch the response and then send it back to the clients. The intention is the location directive coupled with the proxy pass will notify NGINX to request some URI to serve some data. So here we see in our location directive, we have some sort of regex that follows our docs path, and anything following docs will then be replaced in our proxy pass S3 bucket that we see here. So we make a request to help. It really will request help HTML from our S3 bucket. So a regular expression like the one above will match URL encoded new lines. So like the previous misconfiguration, we can also conduct a CRLF injection attack, which means we can put in our own headers again. The proxy pass points to an S3 bucket. We can actually put in our own S3 bucket as a host header and serve our own malicious content from our own S3 buckets. So here, we'll make a request and we see how we add in our carriage return in line 3 characters right before the host header. And because of the proxy pass regular expression, NGINX will then process this and then request our own S3 bucket instead of the original S3 bucket. So now we'll show an example of how this works. So we'll open up our NGINX configuration file. We see here we have a proxy pass to some vulnerable S3 buckets, and then below that is a location directive for our perp collaborator server, which will just show how the host header is split during the attack. So here we make a request to our S3 bucket and it serves very basic data from index.html. And now we'll make a request to our perp collaborator server through the location directive, just to show how this will work. So make the request to index.html. There we see how the server responds. So when we check the logs, we see how there is this host header on line 2, and we want to be able to inject our own host header instead. So again, we'll go to CyberChef. We'll add in our own nefarious POC Detectify S3 bucket. We'll encode new lines, like from the previous misconfiguration, and try to inject that header into the response. So on that S3 bucket, we have some sort of nefarious JavaScript that we want to deliver to the clients or targets. So here, we encode it. We then make that request again in the browser. And then when we check our burp logs again, it should show our host header is now that nefarious POC Detectify S3 bucket, which now we see on line 2. So now how we see that works, we'll actually implement that and try to deliver that nefarious JavaScript on that vulnerable S3 bucket that we showed earlier. So now we'll do that again, and we'll see how now we are able to execute JavaScript and serve our own contents instead of that other content. So the impact again is we're able to inject arbitrary headers into the HTTP response, such as the host header. If we're able to inject our own host headers, we can perform web cache poisoning and serve other malicious contents. We can exploit client-side vulnerabilities like cross-site scripting, and in some cases, even conduct SSRF attacks. The remediation is just to use strict regular expressions and do not allow new line characters in proxy pass. And that is the end of my presentation, and I will welcome any questions in the Slack channel.
Yeah, thank you so much, Spencer. That was a wonderful session. Um, because you were going us through demos and all, so it was very nice. So I think the participants and Spencer can move to the Slack channel. There, Spencer will be answering to all the Q&A questions that you will be asking.
Yep, I can do that.
Thank you so.
I'll be available.
Thank you so much, Spencer. And also thank you all for participating in this session. So you can move to the Slack channel.
All right, thank you.